So now that we've thoroughly defined the word conservative, we're going to take a look at forces that are conservative and forces that are non-conservative. Another way to look at this is forces that, when they act in a system, will conserve energy within the system versus forces that act within a system that don't conserve energy within a system. When I say that energy is not conserved within the system, I'm not saying that we are disobeying the law of conservation of energy. I'm saying that that system has lost energy then to the surroundings. Okay, so let's start with gravity. The work done by gravity in moving an object from one point to another doesn't depend on the path that's taken. So here's a bunch of different paths that an object could take, right? If the object is right here traveling up this path, it would have a height h. And so that means that the work done by that object, or the work done on that object by gravity, would be equal to negative mgh. And that would be the work done by gravity on that object. So that object would have the potential energy mgh. And the work to get it up to that point would be mgh. So let's then assume that we'll call this big H here the height of all of these objects. So let's say you have, we'll call it a roller coaster cart. Right, and this roller coaster cart has mass m. And if that object got brought from our reference point 0 all the way to height h, and it traveled along that distance d, well, the potential energy of that object would be mg capital H. The work that was done to get that object up there would be equal to mgh. And that's true even though it went up that ramp, because the work to lift the object was done in an upward direction with an upward force. So that means that that work only acted in the vertical direction, so it only depends on the height. The same thing could be said for an object that, say that roller coaster fell down, and now it took this much smoother angled path, or traveled up an inclined plane, and now it's up here. Well, the energy that it has is going to be dependent upon its weight and its height, which is still h. So that means that the work to bring the object from down here all the way up here, the work done in lifting that object, was equal to mgh, in spite of the fact that this is a different angle, and this span right here is a different distance than this span right here. Alright, so different angles, different paths. The work done to get that object lifted up was still, the force was in the upward direction, and the displacement of the object therefore only occurred when lifting in that direction. So the potential energy and the work are still mgh. Same thing could be said for an object that was lifted straight up. If the mass is still m, then the force to lift it up was still mg. And the amount of work that was done to make that happen was equal to mgh. So the work still equals the potential energy of the object mgh. Same could be said for an object that follows this fun little loop-de-loop path here. It goes up, it goes down, it spins around. Think about the poor person running around to make that happen until finally the object is up here. Well, the work done in lifting the object was equal to the object's weight and displaced the object to height h, so that's still the work done by that object, or done on that object to get it up to that height. So it does not matter what path is taken, which is really convenient, because can you imagine using kinematics for a path like this, or a non-straight path like that? That would be a pain in the butt. Right? One of the things that makes it helpful to remember this is that the work done to lift anything is always the lifting force and the distance lifted. right? So that's always going to be true because we're talking about the work done to lift, and you only lift in the vertical direction, and all it takes to lift an object is to apply a force that's equal to its weight. So there's the force equal to the object's weight, and here's the distance that you're lifting it up. So that will always be the work done to lift an object regardless of the path that you take. Which is kind of nice because that means it takes the same work to lift an object of mass m vertically a height as it takes to carry it up an incline of the same vertical height. So that means lifting straight up like that will take the same amount of lifting work as lifting it up along this plane. Notice I'm saying lifting work, which means that I'm focusing on the force required to lift it up and the height that you had to lift it. I'm not talking about any work done in the horizontal direction, but one thing that we know is if this is happening with uniform motion, the net work done in the horizontal direction would be 0, because if we have uniform motion, then the net force would be 0. So this brings us to our main point for this lecture, and that is that forces like gravity, for which the work done doesn't depend on the path. So we just showed that it didn't matter what path the object took. The force and the displacement still give the same work. So when the work done only depends on the initial and final position and it doesn't depend on the path taken, these are conservative forces. The conservative forces we're going to be working with mostly are gravity and the elastic force. Both of these are conservative forces because it doesn't matter whether or not the object took a funky path. All that matters is the initial position and the final position, and that determines how much work was done by a force. This is also a really convenient function of a conservative force, and it is that an object that starts at a given point and returns to that point under the action of the same conservative force has no net work done on it because the potential energy is the same for the start and the finish of the round trip. It's easiest to explain this with a spring. I had a spring here. It's gone forever. But imagine, if you will, you have a spring, and this is its relaxed length. Now imagine that you stretch that spring out this amount x. Alright, when you stretch this spring out this amount x, the applied force is going to be equal to kx, and it's going to be equal and opposite to the spring force, which is equal to negative kx. Now, this spring began in its relaxed length where its potential energy, or equals its potential energy, which was 1/2 kx squared negative. Alright, so this is the work done by a conservative force, the work done by the spring force, which would be equal to force times displacement, which is given by this equation. Now, here, since the potential energy of the spring at its relaxed length is 0, that means the spring is doing no work. However, if you pull this spring back from that position, then the spring is doing work, a negative work to the amount of 1/2 kx squared. And that means that once you released that spring, hold on. When you release that spring will oscillate back and forth, and it'll go back and forth, back and forth, back and forth, until its oscillations eventually have it returning to its resting length. And you've seen this happen with a spring. It'll bob or oscillate back and forth, back and forth, back and forth, until it's back at its relaxed length. This is an example of an object that starts at a given point and returns to that point under the action of the same conservative force. We said that the elastic force is a conservative force, and it starts at a relaxed length. The motion gets put into place by giving the spring its negative spring force, and then the work that's done to get it to change back to its relaxed length, well, there's no displacement now, so that means that there is no net force and no net work done. Friction is a non-conservative force, so that means that friction does not only depend on position. For a non-conservative force, the path that you take to get somewhere really matters. So that means that bringing an object up that plank versus lifting an object straight up, now this path matters. Lifting an object straight up, there may be no friction whatsoever involved. However, bringing an object up a plank, right, if friction is a resistive force, then that means this amount of friction is acting in the y direction, and so that amount of friction is going to be doing some work on the object. And so that means that the path that it takes really matters. Let's take a look at this guy right here. This is another example of a path taken. So let's say that this is position 1 right here of a crate, and this is position 2 of a crate. And shown here, there's 2 different possible paths that could be taken. Right? In one situation, the crate is dragged straight across from position 1 to position 2. In that case, the displacement of the object, D, is along that line, and the force of friction is opposite the crate the entire time. So here, the work done by friction is going to be equal to the force of friction times the displacement, and we'll call this D of path 1, so we'll call that displacement, times the cosine of 180 degrees, so because if this is the direction of displacement, all the way over there is the direction of force, that is 180 degrees. So that means that the work done by friction will, first of all, cosine of 180 will always equal -1. So the work done by friction is always a negative amount, and it's negative friction times the displacement. And the displacement depends on the path that you take. We'll call this next one over here, we'll call this one pathway 2. If you bring this box along in an arc, right, the circumference here, the displacement of that, or the distance traveled along that arc, is definitely going to be a different amount than this here. Right here, this is the diameter, this is 1/2 of 2 pi r, or just pi r for the half circumference. So that displacement is larger than this displacement. In that case, at any point along the circle, the friction is resisting the motion forward. So we look at this vectorially and we see that the friction is always, no matter where you are on this curve, it's always at a 180 degree separation from the displacement at that point. See, here's the displacement 180 degrees back, here's our friction. And that's true across the whole path. So the work done by friction for the second path is going to be the force of friction, which this value and this value should be the same, but now the displacement is different. It's a larger displacement, or d2, times the cosine of 180, which always equals which always equals -1. So in the second situation, the work done by friction is equal to negative force of friction times d2. So the force of friction is still the same, The negative direction is still the same for the force, which means that the work getting done by friction is a negative amount. That's a scalar negative amount. That negative work means work was removed from the system, and that was done by the friction. It's easier to think of that when we say that work getting removed from the system is like saying removing energy from the system. But here, path 1 was a smaller displacement, so it's going to be a smaller amount of work done by friction. Here, path 2 was a larger displacement, so the work done by friction is going to be a larger amount. So we can see very easily that unlike gravity, friction is acting against the whole time, and that's for the entire pathway, whereas when we were looking at our objects, gravity did not act when, if you took a zigzag path up, right? Gravity isn't working in the horizontal directions, so that means that occasionally along a pathway it would be the cosine of 90 degrees, and for that moment gravity wasn't acting or doing work on the object as it traveled along that path. However, with friction, if you're traveling along a surface, friction's always traveling, always opposing at 180 degrees the whole time. So friction acts the whole time, and it does work the whole time. So the displacement, or like what path you take with friction, actually matters quite a bit. Friction isn't the only non-conservative force. Tension on a rope is also a non-conservative force. So we can kind of break this down, and we can say that the potential energy is associated with an object's configuration, right? If we lift a box up relative to the ground, that object will have a different potential energy than if it were lower or higher. So it makes sense that there's only one answer per configuration, right? If you've got a reference point and you've got an object, and we'll call this position 1 and this position 2, right? We'll call that y1, and we'll call that y2, and we'll call that y3. Right here, this object is going to have a different amount of potential energy than this object here, and this object is only going to have one potential energy due to gravity compared to this object, which will have a different potential energy due to gravity. So that's always going to be true with conservative forces, but that can't be done for non-conservative forces because it depends on the path. The work that's done depends on the path that's taken. Work will always equal FD cosine 180 for friction. And we're mostly going to be working with and using friction when we talk about our non-conservative forces. So that's going to be something that will simplify some of the work that you do. So potential energy can only be defined for conservative forces. Only conservative forces have potential energy associated with them. Non-conservative forces don't have any potential energy, so that means that when it comes to friction, there's no potential energy due to friction because it depends on the path that's taken. So potential energy is out of the question. So now that we've defined a non-conservative force, what we can do is we can take a look at what that's going to look like quantitatively. So we're going to take a look at the work-energy principle. The work-energy principle is always done with net work. So we're going to consider a situation where there's both conservative and non-conservative forces acting on a system. Right? So that means that the net work is going to be the work done by all the conservative forces plus the work done by all the non-conservative forces, where here we represent WC as work done by conservative forces and WNC as work done by non-conservative forces. And our work energy principle says that the net work done on a system is equal to the change in kinetic energy. So what we do is we take this value here and we plug it in for W net, and we get that the conservative the work done by conservative forces plus the work done by non-conservative forces will equal the change in kinetic energy. We always remember change in kinetic energy is final position kinetic energy minus initial position kinetic energy, or done at two different instances of time. I rearranged the equation because we're taking a look at using the work energy principle to define or explain the function of non-conservative forces. So I solved this equation for non-conservative forces, and I say that non-conservative forces, the work done by them, is equal to the change in kinetic energy plus the work or minus the work done by conservative forces. Since work WC equals work done by conservative forces, and all conservative forces have potential energies associated with them, so what we could do is we could use the relationship of the work done by a conservative force, and this is something that we have already defined as the work done by a force is going to be equal to negative the change in the potential energy that has just taken place. So if we're going to plug in negative delta PE for work done by conservative forces, then that negative WC becomes a positive delta PE. So the work done by non-conservative forces is going to be equal to the change in potential energy plus the change in kinetic energy. Another way to say that is that the work done by non-conservative forces is equal to the total change in potential and kinetic energies. In order for this equation to work, all of the forces acting on a system must be included, so that means that we have to consider when we're looking at this any possible forces that could be acting that could affect the total or net work done on the system. Since we're taking a look at the net work done on the system, if you know that there is force acting in one direction and an equal and opposite force acting in another direction on that system, you know the net work of those two forces would be 0, and those could be removed from the equation.